Next, we'd like to give the floor to a teacher from University of Science and Technology of China, Mr. Zhang, to give us a presentation on their research.
Okay. Hi, everyone. My name is Kai Zhang. I'm from the University of Science and Technology of China. Today, my talk is about building high-performance network systems with innovative hardware and software techniques. I know this topic may be too big, but actually, I'm going to talk about two projects. One is about a paper we published last year on the VLDB conference, and one is about a project that is collaboration between USTC and Intel. Okay, this graph shows global business data, its growth trend until 2020. This is estimated by the Oracle, and the volume of the business data worldwide is expected to double every 2 years. Moreover, this graph shows the data from IEEE Higher Speed Study Group. It shows that the core networking speed is doubling every 18 months, and the server I/O speed is doubling every 24 months. So both the data volume and the networking speed is growing so fast, and we're using this. Currently, we're using CPUs, general purpose CPUs, and operating systems such as Linux and FreeBSD to build network systems. So current operating system and hardware may be not enough for the future network device. So we have new hardwares, including GPUs, and Intel is also integrating GPUs into CPUs, and there is a Xeon Phi, which makes the world's fastest supercomputer. And for the operating system, we have new drivers such as DPDK, NetMap, and so on. So the question becomes how to utilize these new hardware and operating system tools to build the next generation network system. Because the drivers such as DPDK unleashes network I/O speed, right? And this new hardware generally needs new algorithms and new data structures. So the system needs a redesign, a completely redesign. In this talk, I'm going to talk about two systems. The first is called MicroKV. This is published on a very large database conference last year, and it's currently the KV store system with the highest throughput. The second, I'm going to talk about integrating DPDK into Snort. This is a cooperation between USTC and Intel for educational purpose, and it's going to be a course lab for the advanced computer networks. The first, I will talk about MicroKV. So what is key-value store? It is a simple but effective method to manage data where a data record is stored and retrieved with its associated key. It has a variable type and length. It has simple no schema, and it can ease the software development for many applications. Examples including the DynamoDB from Amazon, RocksDB from Facebook, LevelDB from Google, and the famous Memcached and Redis. So the interface of key-value stores are simple but powerful. For example, you can use this set to set the key and its associated value into the system. And you can use this get to get the value with its specific key. Here's an example. A client may send a query, a get key query to the key value store, and it looked up the key value object through the index data structure, located it in the memory or disk, and then it sends the value back to the client. Okay. So the keys and values can be different things. For example, if you log into Amazon, the key can be your customer ID. And once you logged in, your information such as the credit card information and the buying history are brought to you so that the website can recommend you new products. And other examples such as user ID and your photos posts in Facebook and Twitter, and even movie or song can be a value. Okay, we will show the workflow of a typical in-memory key-value store. The first is network processing. The second is the memory management. Third, index operations. And the fourth, access the value in the memory. So the network processing includes TCP/IP processing and query parsing, which is the application layer parsing. And we can get three types of operations, including delete, set, and get. If the memory is not full, and this for set query, if the memory is not full, we will allocate a new memory for the key-value object. And if the memory is full, we will evict an existing key-value object to store the new object. Then we will perform the corresponding index operations, such as delete, insert, or search. If it's a get query with the search results in the index, we can get the location of the values, then we read it from the memory and send it to the client. We did a quantitative analysis of Mika, which is the state-of-the-art CPU-based implementation. It's published on SDI 2014. We found that the network processing and the memory management takes only a small portion in the overall execution time. Of course, it's with DPDK. It's worth noting that without DPDK, the network processing was the bottleneck of the key-value store system. So now, with DPDK, it's a totally different situation. We found that the index operation has become one of the major bottlenecks for key-value store systems. And the last is the access value in the memory. It depends on the speed of DRAM. When the key-value object gets larger, the more sequential memory accesses are needed. So the larger portion it will take in the memory, in the overall execution time. So why does index operation take such a large portion in the overall execution time? We did a detailed analysis. We found that a query will go through the first two parts, including the network processing and the memory management. Then it will find the key-value object in a hash table, which includes several random memory accesses. Then it can access the value in the memory. We found that the random memory accesses are very expensive. These blue points show the execution time, shows the time of sequential memory accesses. And we found that two random memory accesses, the time of two random memory accesses equals to the time of 7 sequential memory accesses. And the time of 3 random memory accesses equals to the time of 16 sequential accesses. So we find that current solutions on CPUs are unable to solve this issue because the key-value store, the working set of key-value store is very large, which is generally hundreds of gigabytes, but the CPU cache is very small. So it's unable to keep the key-value objects in the cache. Second, use the conflict linked list. It's not easy to predict the next memory address with prefetch. And when we want to use multi-threading, but the hardware threads in current CPUs are very limited, and the number of outstanding memory accesses depends on the number of misstators holding registers. So as a result, CPU spends a large portion of its time idling, waiting for the data to be fetched from memory. This is very inefficient. And we propose MegaKV, which addresses two issues. The first is the large number of queries. The second is the random memory access delay. So for the 4 parts in the workflow, we apply the state-of-the-art techniques for the 3 parts, including DPDK. And for the index operation, we offload the index data structure and its operations out to the GPU. Our goal of building MegaKV, the first concern is throughput, because it's very critical in the big data environment. And we want an acceptable latency. For Facebook and Amazon, 1 millisecond latency is good. So our goal for MegaKV is to maximize the throughput subject to an acceptable latency. why GPUs? Here is a comparison between CPUs and GPUs. This graph is borrowed from NVIDIA. As you can see from this figure, a very large area of GPU die has been devoted to massive ALUs. And GPUs have a much higher number of transistors, thousands of cores, and about 5 times higher memory bandwidth. So this CPU and GPU is the ones we used in our experiment for the MegaKV. For the architectural characteristics, GPUs have 2 advantages for key-value store systems. The first is its massive processing units to address the large number of concurrent queries. The first, the key-value stores, the operations in the key-value stores are simple and independent memory access. So the thousands of cores in the GPU is able to do this job the parallel processing. The second, the GPUs can effectively head the random memory access latency with massive hardware threads and zero-head thread scheduling. This is hardware implementation in the GPU. So here's an example. This is instructions from 3 threads in the instruction buffer. The GPU core executes these instructions one by one. When there is a cache miss, it will switch to another thread with 0 overhead after the memory request is issued. Okay, cache miss, and it will switch to another thread with 0 overhead. This is the basic design of MegaKV, which is divided into a 3-stage pipeline. The first stage is pre-processing. Second stage is GPU processing and post-processing. So we use DPDK to do the packet I/O, and the network processing and memory management are then to the pre-processing stage. And we then the index operation and its data structure to the GPU. The post-processing stage reads the value in the memory and sends them to the client. Also, we use DPDK. So with the fast incoming queries, we process each query one by one, and we batch them in a buffer. Once the batch size reaches limit, we offload it to GPUs for parallel processing. And for get queries, the GPU process results are the locations of the key value objects. So we do the post-processing and read the value in the memory and send them to the client. And using GPU is not easy. Actually, there are 3 challenges for offloading the index operation to GPUs. The first is that GPU's memory is small. It's only about 10 gigabytes. But the working set I have talked about earlier is hundreds of gigabytes for in-memory key-value store. The second is the PCIe bandwidth is very low, and it's generally the bottleneck of GPUs if large bulk of data needs to be transferred. Third, GPUs are very efficient to handle variable length data. I have shown before that key-value objects are generally variable length. The keys and the values, its length is hard to say. So it will cause imbalanced load between GPU cores. But the GPU execution time depends on the slowest thread. So this will result in an underutilization for the GPU. Our approach, first, we compress the variable length keys to fixed length signatures, which is 32 bits. This addresses challenge 2 and 3, the PCIe bandwidth and the variable length data issue. For the conflict linked list, we use GPU optimized Cuckoo hash table to store key signatures and value locations in the CPU memory. So this addresses challenges 1 and 3, the GPU memory capacity issue and the variable length data. If we have variable length keys, we first compress them into fixed length signatures. And then we store them into GPU Cuckoo hash table with their value location. So if we want to search for a key, it should also be compressed into signatures, and we search it in the GPU cool hash table, and we find its location and to locate the object, key value object in the main memory. After key comparison to confirm the match, we send the value to the client. Okay, this is a hardware platform that we used. We use 16 CPU cores and 4,608 GPU cores and 40 gigabits per second network card. So this blue bars show the fastest CPU-based key value store, which is a Mika published on SDI last 2014. And this green bar shows the throughput of MegaKV. So for all 4 data sets, we are about 2 times higher. The throughput is about 2 times higher than that of Mika. And in this graph, we measure the round-trip latency of MegaKV. The 50th percentile latency and the 95th percentile latency are 256 and 390 microseconds respectively. And that in Facebook is reported to be 300 and 1200 microseconds. So although we use GPU, there's a batching in the GPU that increases latency. We are still below the requirement in the production systems such as Facebook. So it's acceptable, although it's a little higher than the CPU-based version, but it's acceptable. So I will talk another project. This is about integrating Snort into DPDK. It's a collaboration between Intel and USTC. So what is Snort? It's a multi-mode packet analysis tool. It can be used as a sniffer, a packet logger, or forensic data analysis tool, or an IDS. So it's able to perform network traffic analysis both in real time and for forensic post-processing. It has several metrics. I think the most important is it should be fast. It must have a high probability to detect an attack on a high-speed link, right? And it should also be configurable, so users can write new rules in the to expand the rule set. This is the Snort architecture. The first is the packet I/O, and including the rest is the packet decoder, preprocessor, detection engine, and so on. But we find that the cost of packet I/O without DPDK is very huge. This is bought from. These numbers are bought from papers that are published previously. For packet I/O, about 1,200 cycles are needed. And for the packet detection, Snort generally requires 400 to 25,000 cycles. But for 10 gigabits per second link, the minimum size of packet is our budget only 1,400 cycles. So we see that our budget is very limited, and there leaves no space for the detection, right? This is because Snort was designed to detect attacks on the 100 million bits per second links. But the current network is growing very fast. So it has reaches 10 gigabits per second and 40 gigabits per second. So Snort has become incapable of detecting intrusions on current backbone or data center networks. So our work is to integrate DPDK into the network I/O part of Snort. Actually, Snort has noticed this issue, and from Snort 2.9, it introduces it's called DAQ, Data Acquisition Library for packet I/O. So people can implement more packet I/O methods into Snort. Currently, it supports PCAP, AF packet, NetMap, and IPFW. So we are going to integrate DPDK into Snort. We find that DPDK is able to significantly reduce the packet I/O to only 80 cycles, so that CPU have more time for other tasks such as packet detection, which is the most important task for Snort. And this is the hardware we use and software. So in our experiment, we measure Snort in two modes. The first is the passive mode. In the passive mode, Snort is bypassed in the network, and it uses a promiscuous mode to receive all the packets from both sides to analyze traffic. In the inline mode, it filters packets and it blocks the malicious packets and do not let it go to the servers or clients. So this is Snort throughput without DPI. So we only want to measure the packet I/O performance of DPDK. So this uses 64 bytes packets, and there's no DPI here, and it is measured in the inline mode. So we can see that the DPDK performance is very stable. It reaches 14.88 million packets per second, which is the highest throughput for 10 gigabits link. But the netmap is not stable, you see. And this graph shows the latency of DPDK and netmap. We can see that the latency of DPDK for each packet is also very stable. It's about 0.15 microseconds, and it's about half the latency of netmap. So we choose the right thing, right? And this works in the passive mode. We measure the performance of 4 methods currently in the Snort: DPDK, netmap, AF packet, and PCAP. We use the trace from our university gateway, and we find that new drivers such as DPDK and netmap can significantly boosting the throughput of Snort, about 3 times higher than AF packet and PCAP. So that you see the packet I/O part is very important in high-performance processing systems such as Snort. So here we come to the summary. So MagKV provides the highest throughput. It's all because DPDK has unleashed the I/O speed, and we have the opportunity to identify that index operation has become the bottleneck in memory key value stores after DPDK is applied. So we use GPUs to accelerate it. And the second is we integrate DPDK into Snort. It's going to be a cause for advanced network technologies in USTC. Thank you.
有没有问题？
Kyung-Soo Park from Kaistan. Interesting talk. So in your key value storage, I think it's not just a read only, right? Typically, you can actually update the key value, insert and delete.
Yes.
And then how do you actually support the kind of modification to your table in GPU? It may not be very efficient, right?
Currently, in-memory key value store works as a cache. So there is a insert, delete, or search. Yes, there are 3 types of queries. And you mean to change the current key value item? You mean?
Yes. So you read some key value as well as at the same time you update the index as well, right?
Yes.
In typical real world application. So is your performance actually including both of these workloads?
Yes, all of the workloads. So if there is a set query, we will just insert the key value objects into the memory. And if one wants to change the value of an existing key value item, we just have 2 operations to the index. One is delete the existing one, and the other is allocating a new memory key value objects and insert it to the index again.
And that's done in the GPU?
Yes, that's done in the GPU. We perform all the index operations in the GPU because its data structure is stored in the GPU memory.
Okay.
Yeah.
Can I ask one more?
Yeah.
How do you actually handle the signature conflict So you create the signature 32-bit.
Yes.
Maybe there might be conflict, right? So
Yes.
different keys actually collision actually.
Yes,
Yeah.
yes. So when the signature conflicts, actually, before we send, we get the location of the key value object from the GPU processing, and then we read the key value object in the CPU memory, in the host memory, and before we send the value to the client, we first match the keys to confirm the match. You know, the key is stored with the value in the memory. Yes, it's with the value. So before we send the value, we confirm the match by matching the keys.
So you assume that the random access to the actual location is not the bottleneck. You random accessing the hash table is the bottleneck, right?
What? Pardon?
So you with GPU you reduce the time for looking up, right?
Yes.
So the hash table lookup.
Yes.
Is you assume that's a bottleneck instead of actually retrieving, reading, and then sending the random the actual data located at random, right?
Reading the data is actually, if the data size is very small, you can consider it's random memory access.
But you have to go to the random location, right?
Yes, but so the GPU memory is very small, so you have to store all the key value objects in the CPU memory, right? So I think it's inevitable. So after we solve this issue, we offload the index operation to the GPUs. Actually, now the access value in the memory has become the major bottleneck for the MegaKV the system we built. Yes, so it's still unsolvable. It's not solved by us. Yeah.
Use DPDK in the classroom and let students do some experiments with DPDK, which is a very good trend.